talk before the coffee break. Biju will talk about study of the radio spectral properties of 4Th35.06. Setting up the microphone. That works?
Yes.
Okay. It's all yours.
Hi. So I am happy to present here some of the results of our radio and optical studies on the radio source 4C35.06. So these are my collaborators, and 5 of them are here in the audience. First 5 of them are here in the audience. So the outline of my talk is like this. So after introduction, I will be discussing the optical and radio observations on the source, followed by results and summary. Now this radio source 4C35.06 is very peculiar because it is occurring situated at the center of the galaxy cluster, central region of the galaxy cluster Abel 407. You can see here. So here you can see a complex ensemble of 9 galaxies. These are embedded in a diffuse extended stellar halo. And these 9 galaxies are having redshifts from 0.046 to 0.049. And so in projection, the projected separation in projection is also very less. You can see that 7 galaxy pairs in this region are separated by less than 10 kpc in projection. And this region is already studied by Schneider and Gunn in 1982, and they proposed that this is in the emerging state of a CD galaxy, and they proposed that this will emerge into a full-fledged CD in 2 billion years. So this study on this source is very important, as this source is an ideal case for studying the growth and evolution of supermassive black hole in CD galaxies and triggering of AGN. So I am happy to present some of the slides from GMRT, maps from GMRT. Here our radio observations are mainly from GMRT, and optical observations from Ayuka-Giravelli Observatory 2-meter telescope, and 3 sources were observed using a Palomar 5-meter telescope. And you can see that this radio morphology is very peculiar. So this is the 610 MHz radio map taken from GMRT with 5 arcsecond resolution. So radio morphology appears very peculiar. This is the first radio map clearly revealing the structure of this source. More on this morphology can be discussed in the coming slides. And you can see that there are 3 radio peaks shown by red crosses here, and they are falling on these galaxies G6, G2 and G5. The inset image shows that several galaxies. And from the spectroscopic observations, we have determined the black hole masses of these central galaxies, and we found that all are of the order of 10⁸ solar mass. So these are the GMRT maps we obtained, we prepared. So we have 3 observations. Observations at 3 frequencies: 610 MHz, 235 MHz, and 150 MHz. And this is the 610 MHz map. So you can see that here it bends into an arc from A2 to B2, and so the linear sizes varies from 230 kPa to 400 kPa, from 610 MHz to 150 MHz. When you go to lower frequencies, you can see more extended emissions on both sides. So here also there is more extensions, here also you can see more extensions. And when you go to 150 MHz, this ends into a knot here, so similar to this point. And this region, this extended region is noted as D2, and this extended relic region is noted as D1. So we have more discussion on that particular regions later, on the later slides. And the flux densities are varying from 1.7 Jansky at 610 MHz to 6 Jansky at 150 MHz. So the integrated spectrum shows a Stick spectral index of -9, 0.92 from 26 megahertz to 4.9 gigahertz, and the spectral indices of the outer diffuse regions are also calculated. You can see this blue marks that corresponds to the relic region D1 and pink ray points correspond to the region D2. So that shows extrinsic spectrum minus 1.79 and D2 region shows minus 2.1. This is the spectral index maps we have prepared between 610 MHz and 235 MHz in the left panel, and the right panel that prepared between 235 MHz and 150 MHz. You can see very steep spectral index up to minus 2.5. We have estimated the spectral age from the spectral break frequency in the relic regions. So we found that this break frequency falls in both the regions almost around 304 megahertz, and the spectral age is calculated as some 80 to 210 mega years. And we can discuss more on the jet precession. The inset image is shown that of the famous microquasars SS433. So this image is the 610 megahertz 5 arc resolution image from GMRT, and you can see it's inverted gray. It is in inverted grayscale. You can see that you consider these regions A2 and A1. You can see that the jet twists into an arc here from A2 to B2. The similar feature you can see from A1 to B1 here also. And also at lower frequencies, if you can see more extensions from B2 to D2 here, and similarly from A1 to D1. So as a whole, the jet structure moves like this, coming back and flows like this. So some similarities you can observe as in the case of this microquasar SS433. So this indicates that the relatives just behave in the same way, ranging from stellar mass black holes to supermassive black holes. So helical structures are generally indications of jet precession. So two possible mechanisms for jet precession: one is the binary black hole model and the other is the Lenz-Thirring effect. So as you know, in the binary black hole model, the accretion disk of the AGN can be precessed by the torque exerted by the combined black hole, and this will lead to the precession of the jet. Now in our particular case, the closeness of the galactic members and the rotationally symmetric helically modulated large scale jet structure and together suggest this site ideal for the search of some binary supermassive black hole system. So the Lenz-Thirring effect comes into play. So when the spin angular momentum of the black hole is misaligned with the angular momentum of the accretion disk. So we have estimated the precession timescale of the jet system for a black hole of mass 10 raised to 8 solar mass with the different values of the specific angular momentum A and body invitation radius RBP. So we found that the precession timescale obtained are of the order 10 raised to 5 years when the specific angular momentum value is A is equal to 0.1 and multiplication factor is 10 cube, and 10 raised to 8 years when A is equal to 0.1 and F is equal to 10 raised to 4. That means the precession timescale, to match with the radiative age, the black hole should be very slow spinning with and we have to consider a high Bardeen-Peterson radius. And these are my summary. So this extremely steep spectrum relic region suggests that this is due to some previous epoch of AGN activity, and such AGNs in the ultrasonic spectrum, relic spectrum, are very rare and form an interesting population for understanding the life cycle of relativistic jets. It's an ideal case for studying the formation and evolution of supermassive black holes in CD galaxies. So still we don't know whether there is a binary black hole or the precession is due to Lenz-Thirring effect. So anyway, this is an interesting source for further study.
Thanks for staying on time. Other questions? Yes, Catherine.
Thank you very much for showing us that gorgeous radio image. I was wondering if you could explain where you were getting your precession timescale from.
Oh, precession timescale? Yes. Yeah, actually we calculated the precession timescale So you need the equation or something like that.
I'm wondering whether the precession timescale that you present here on this slide comes from fitting the form
No.
of
So we
the
have
appearance
used
of the
this,
jets.
This paper.
Okay,
So we have
thank
used
you.
this.
I'd like to make a suggestion in that case, which is that you take the precessing jet model from Gelming and Johnson 1981 and actually fit it to your radio image, because the way that jets can actually appear when they're precessing can be quite amusingly counterintuitive, and it's well worth fitting it to see what you might learn from that. And that would be a different handle on what the precession timescales are, and indeed the jet speeds.
Okay. Yes. Well,
it's connected to that precision. So I agree, because I was about to ask the question, like you're getting the equivalents from the SS443 and your AGN. See, the bulk Lorentz factors are very different.
Yeah.
Okay, and so the light travel time effects, the relativistic your relativistic effects will be more prominent in your AGN jets compared to your microquasar, that SS443 jets. So that I'm not sure. So can we use the same model, same precision model, which is used for SS443 to fit for the radio galaxy?
Sure you can.
Oh, thank you.
that's a quick discussion. Yeah. One last question, please.
I'm actually thinking about the difference between precession period and the age of the source. It looks like the precession period.
Yeah, actually
So the age of the source is.
We try to see some match is there between this radiative age. So this is from D2 to some precession cycle we imagine. Yeah, we consider it, and we try to check whether the time is matching or not. Only that much.
Yeah, still that is very small compared to the precession period. So
yeah, so this is of the order of 10 raised to 8 years, and you can see that the precession time scale using a lens-ring effect. Usually A is taken as can be taken from 0.1 to some high values up to 1 maximum values, and usually this multiplication factor is taken less than 1000.
Okay. Well, I think we'll have to stop the discussion here because